Alright, so in previous classes we dealt with Boyle's law and Charles' law. Let's look at the third one there called the ideal gas law. You take down this. Ideal gas law. Take down. This states that ideal gas law. This states that the pressure of a gas varies directly. The pressure of a gas varies directly as its absolute temperature varies directly. You can say with its absolute temperature at constant volume. Pressure varies directly with its temperature at constant volume. That's the ideal gas law. Pressure of a gas varies directly as its absolute temperature provided volume is kept constant. So look at this. So what we did last time, we said pressure is P, volume is V, temperature is T. So if I say pressure varies directly, becomes this as what there is temperature. So pressure varies directly as temperature here. Of course, we said to take out this man here, you introduce an equal to and put what there a constant with T. From here now, make K substitute the formula. I'll divide here by T, divide here by T. This cancels this. So I have that K is equal to what there? P all over T. So that's your constant when it comes to gas law. That pressure over temperature is equal to your constant. Alright. If I'm considering two different gases, or perhaps the gas at two different points, then it means that P1 all over C1 is equal to what there? P2 over what there? T2. That's okay. P1 all over T1 is equal to P2 all over T2. I have this. A sample of hydrogen gas has a pressure 700 mmHg, that's millimeter mercury. Has a pressure 700 millimeter mercury. Has a pressure 700 millimeters mercury with a temperature of 30 degrees Celsius. With a temperature of 30 degrees Celsius, full stop. Calculate the new temperature. Calculate the new temperature. Pressure, please. Calculate the new pressure. Calculate the new pressure of the hydrogen gas. Calculate the new pressure of the hydrogen gas if the temperature was raised to 150 degrees Celsius. If the temperature was raised to 150 degrees Celsius at the same volume. Let's say you're going to turn in an exam. You have options A, B, C, D. Which one do you think, without solving, should be the answer? Let's say give me this question in an exam. This particular question in an exam, and you're not to solve this. Which of these do you think will be the answer, and why? Huh? That's what? 720. Why 720?
Since the new version, the former one was 700, just assume that the new version will be
Alright, so listen up. Listen up. I said this in the last class. I said when it comes to variation, always note the type of variation. If two things vary directly, as one is increasing, the other one also does what there also increases. That's what we said. For a case like this is a case of direct variation. I said for direct variation, if one parameter is increasing, the other one also does what there also increases. Also look at the second one called inverse variation. For inverse variation, as one parameter increases, the other one does what there reduces. We explained it in the last class. So for the fact that this is a question on direct proportionality there, if one is increasing, the other one must increase. Look at the question there. My first temperature there was what? 30 degrees Celsius. It increased from 10 to what there? 150 degrees Celsius. So that's about an increase. What does it mean? It means that my pressure should also do what there? Also increase. So plus minus, whatever answer I should get should be what there? Greater than 700. That's the concept. So if I look at this now, the only option that I have that's actually greater than 700 is what there? Is 720. That's the concept. That's the concept. Please, always note your variation. If it's direct, as one is increasing, the other is also what there? Also increasing. Right? Alright, let's start this one. Solution. So task 1, list out given parameters. List out given parameters. So I'm giving what there? I'm giving my first pressure P1 as 700 millimeter mercury. My first pressure there is 700 millimeters mercury. I have this. What is that? They said at temperature T1, how many there? 30 degrees Celsius. Listen please. I said pressure has different units. Alright? One of them was millimeter mercury. Like so when it comes to conversion, for gas law, the only way it converts is what? Is temperature. So hence, I'll convert this from degrees Celsius to Kelvin. How do I do that? It becomes 30 degrees plus what there? 273. So this is a constant. Add this to this, you get your answer in Kelvin. So if you add up this 3, what do you get there? 303. 303 Kelvin. If I do this plus this, gives it 303. That's my conversion. Next one again, it said calculate its new pressure. So the P2 is unknown. The new pressure P2 is unknown. It said if the temperature was raised to, so I'm giving a second temperature that is raised to how many there? 150 degrees Celsius. Obviously, just like this now, I'll convert to Kelvin. So it becomes equal to 150 degrees plus 273. That gives you what here? 324 Kelvin. Correct? Yeah? 43 Kelvin. Alright, so if we have this now, we have to find the value of what? P2. So just recall your formula. Recall that we said P1 over T1 is equal to P2 over T2. We want to find T2. So what do we get now? We want to find P2 per se. So make P2 subject of the formula. What do you get now? This times this times this. So I'm having this and this. So P2 times T1 is equal to this times this. P1 times T2. Obviously, to make P2 stand alone here, I'll divide them by T1. I'll divide them by T1. This will cancel this. So it means that P2 should be equal to the value of P1 times T2 all over T1. In quick value, I have that P2 is equal to P1. P1 is what? 700 there plus T2. T2 is 423 times 423 all over T1. T1 is about 303. I'm having 303. Please give me final answer. What do you have? 9 what?
977
point. 0.23. What will be your unit? Millimeter mercury. Please also be punching this. Is it correct? I posted one video on YouTube. Then I saw a comment on YouTube. So I just supposed to just drop. The notification just dropped. First I saw there was, with all due respect, sir. I was like, it's gonna comment on YouTube. So I went to open YouTube. It was just to say, with all due respect, sir, the answer is 42 point something, not 4.2 something. And I replied, that's okay, fine. Thank you for the correction. And expect better content. But the fact is that you don't give me the answer. So what that you tell me, it's what I report. And it's being recorded. That's what you see on YouTube. So please stop giving me wrong answers. Once somebody punches, make sure you cross check it. So now found out that with all due respect, sir, again. Right? Right, so that's the concept. So it's actually easy, right? Just know which one to use. Know when to use P1 V1 equal to P2 V2. Know when to use V1 over T1 equal to V2 over T2. Know when to use P1 over T1 equal to P2 over T2. That's like the concept there. Don't forget, in this case, the only thing you're converting is temperature. Alright, let's proceed please. Example. Question? Yeah. Yeah, that's fine answer. Huh? Yes, it's not here. No, so was an assumption now. Hold on, so was an assumption. I was trying to tell you something. What was that? I said, I'm expecting my answer to go there bigger than this initial value. That's what I was saying. Of course, you can see it here. It's bigger than that value. Right? So it's not saying this one was just my assumption. These are this. Okay. It's no. Example 2, please. Example 2, please. Sorry, let me clean the board, please. Let's look at something called the ideal gas equation. Look at the ideal gas equation. Alright, take that one, please. The ideal gas equation is obtained. The ideal gas equation is obtained from the combination. The ideal gas equation is obtained from the combination of both Charles and Boyle's law. It's obtained from the combination of both Charles and Boyle's law. Both Charles and Boyle's law. Come up. And it describes the behavior of an ideal gas. And it describes the behavior of an ideal gas. And it describes the behavior of an ideal gas. Full stop. Mathematically, that should be in a new paragraph now. Paragraph. Mathematically, comma, the ideal gas equation is expressed as mathematically, comma, the ideal gas equation is expressed as. So look at this, please. Look at. We said for ideal gas law, I'm combining two laws, which are Boyle's laws and then Charles's law. For Boyle's law, we said P1 V1 is equal to what there? On behalf, let's just say PV is equal to what there? Constant. So it's Boyle's law. For Charles law, we say what there? V over what? C is equal to what there? Constant. This is Boyle's law. This is Charles law. For ideal gas law, we are combining both of these. So hence it becomes this. So for ideal gas law, mathematically, I have this. These two from Boyle's law becomes PV all over from Charles law. Now for Charles law, I already have V over T. you don't go and say V again all over T. No need. Why? I don't have V here. Just put your all over T. It becomes all over T is equal to constant. This is your ideal gas equation. So this is the ideal gas law. That PV all over T is equal to constant. This is the ideal gas equation. The constant, continue. The constant is represented by R. R, there is capital R. Capital R. The constant is represented by R there. That's capital R. Hence, P V all over T is equal to R. I have it. Hence, PV all over T is equal to R. Okay, if I move this one here, over here, what do you get there? Means that PV is equal to what there? RT. Alright, PV is equal to RT. Let's proceed please. For N, for this way, for N moles of a gas, for N moles of a gas, for N moles of a gas, the equation becomes PV is equal to nRT. Observe the n is small n as compared to the height of RT. So look at what I'm writing down. The n is small compared to the height of RT. So PV is equal to what? nRT. The equation above is referred to as the ideal gas equation. Let's come down here. The equation above is referred to as the ideal gas equation. The equation above is referred to as the ideal gas equation. Full stop. Making R this subject of the formula, making R subject of the formula, we have, so I want to make R subject of the formula. What do I do? Divide here by NC, divide here by NT. This will cancel this. This and this is off. So R becomes from there. PV all over there, and it's very important. R is equal to PV all over NT. This R is a constant. It has a constant value. In Jamb, they might give you the value, or they might not give you the value. Right? So when they give you value or don't give value, sometimes you have to cram. In quotes, we have to cram if we have to. Right? Let's look at this please. If you're done with this, paragraph. If you're done with this, paragraph. At STP. What's STP? Huh? And pressure. Standard pressure. Very important please. Right? At STP, comma, we are at STP, for STP, what's the value of T? What's the value of T for STP? T is actually 0 degrees centigrade for STP. If I have 0 degrees centigrade now, convert it to Kelvin, what do you get? It becomes equal to 0 plus what there? 273. That is what there? 273 Kelvin. This is standard temperature. Alright, so we've got the standard temperature. Let's get pressure. And pressure is the standard pressure, and pressure P is is equal to what there? 1 atmosphere. 1 atmosphere is standard pressure. What's the value of 1 atmosphere in terms of Pascal? The value is 101,325 Newton per meter square or Pascal. The last time we said this and Pascal, same thing. Alright. Alright. Please, so let's proceed. So we said at STP, T is 0 degrees Celsius, that's 273 Kelvin. At STP, pressure is 1 atmosphere, that's 101,325 Pascal or Newton per meter square. Also, for 1 mole of a gas, that is N equal to 1. For 1 mole of a gas, that is N equal to 1. For 1 mole of a gas, N equal to 1. And volume V being equal to 22.4132 liter per mole. All right. Then at STP, what's R? At STP, what's R? So R will be equal to what is it? R will be equal to P. For P, you're using the value of P to what? Atmosphere. That's we said this is equal to P. That's 1 times V. This 22.4132 all over N. Number of moles, we said 1 times T. What's T there? 273. Please give me this value. What do you guys? It's what? 2 ones.
Yes.
So how much is what? Liters atmosphere per mole per Kelvin. So the value of R is a constant. The value is 0.0821 liters mole or liters atmosphere per mole per Kelvin. That's the value of R. Alright. Note please, at STP, pressure is 760 millimeters mercury. I mentioned this in last class. At STP, pressure is 760 millimeters mercury, temperature is 273 Kelvin at STP. So at ST, it's called standard temperature and pressure. So not really volume. So there's no really ST volume, alright? At STP, 2 things are standard there. Number 1 is temperature. Temperature is 0 degrees Celsius. In terms of Kelvin, because what there? 273 Kelvin. Pressure is what there? 760 millimeter mercury or 1 atmosphere. Alright, example please. Example. Calculate the volume of a certain mass of oxygen. Example. Calculate the volume of a certain mass of oxygen at STP. Calculate the volume of a certain mass of oxygen at STP if it occupies 4.48 liter, that's L, 4.48 liters at 27 degrees Celsius and 750 millimeters mercury and 750 millimeters mercury and 750 millimeters mercury. So look at it. Look at what I have there. I'm looking for what parameter there, please. What parameter am I looking for? Volume. The volume there, is it volume 1 or volume 2? Huh? Will it be V1 or V2? Which of them? Huh? Will it be V1 or V2? V1. Alright. So the first case is they said at STP. That means the STP condition becomes what there? My initial. They mentioned STP first before the other ones there. So my STP condition becomes what there? Initial. So first of all, at STP, what temperature there? T we said, or T1 in this case, is equal to what there? 273 Kelvin. That's case 1. P there, P1 is equal to what there? 760 millimeter mercury. So find the volume at this point. So V1 at this point is unknown. This is at STP. Alright? Alright. So for the non STP condition, what do you get there? They gave you 4.48 liter represents which parameter there? Liter is which parameter? Huh? Volume. Alright, so I have V2 and V was there? 4.48 what? Liter. What do you get there? They give you T2 as what there? 27 degrees Celsius. Convert it to Kelvin. I have that T2 is equal to 27 plus what there? 273. What do you get there? 300 Kelvin. What is again there? That was P2. Have you? How many there? 750 millimeters. Then say find V1. Obviously, this one becomes equation on the ideal gas equation. So recall that we said V1 over T1 is equal to what then? V2 over T2. We want to get the value of V1. So make V1 subject of the formula. How do you do that? This one comes this way. This one goes this way. So this times this. I have V1 T2 is equal to this and this. V2 T1. So I want to make V1 stand alone. I'll divide them by these two. That's P1 T2. Divide them by what? P1 T2. This cancels this and this. Hence, I have that V1 is equal to the product of P2 times V2 times T1 all over P1 times T2. So impute value P2, what's P2 there? 750 gives you 750 multiplying V2. V2 is what? 4.48 times what's T1? 273 all over what's P1? 760 into what's T2? 300. Please give me numerator only. Numerator only. What do you get? 917280 for numerator. All over. Give me the denominator. What do you get? 228000. Huh? So V1 is equal to what do you get? Let's confirm this value. What do you get? 4.02. What's your unit? Of course, V2 or V1 will take the same as what there. V2. V2 was a what? Is that so because of here? Alright, so that's your tax then. That's it. Example 2. A given mass of N2, that's this. What's N2? What's N2? Huh? What's N2? Huh? Is that? A given mass of N2 is 0.12 dm cubed. So we tell that N here is nitrogen. This means a molecule of nitrogen. I should be telling you this. A given mass of N2 is 0.12 dm cubed at 60 degrees Celsius. At 60 degrees Celsius. And 1.0 times 10 to the power 5 10 to the power 5 Pascal, full stop. Find the pressure at the same temperature. Find the pressure at the same temperature if the volume is changed. If the volume is changed to 0.24 dm cubed. If the volume is changed to 0.24 dm cubed. Full stop. So help me please. Help me get out answers please. Given, what do you have there? Huh? You have what there? V1 has been equal to what? 0.1 to what? 2.12 dm cubed. What else do you have there? T1 has equal to what there? 60 degrees Celsius. Please convert 60 degrees please to Kelvin. What do you have there? So add 273. What do you get here? This? Right? Okay. What's next then? P1 is what then? 1.0 times look at what there? 5 Pascal. Okay. What else again there? Find the pressure. So P2 is unknown. Find the pressure at the same temperature. What's T2? What's T2? We said at the same temperature. If the same temperature, what does it mean there? T2 is equal to what there? T1, which is equal to 77 or 333 Kelvin. They said volume V2 is changed to what? 0.24 dm cubed. Find what there? P2. Alright. From here, what's your parameter here? You have that P1 V1 over T1 equal to what there? P2 V2 over what there? T2. Alright. Want to get what there? P2, I mean? What will be P2 there? Now listen. For this case, please check. Which parameter is constant here? Check. Which parameter is constant? They said 1 remains. For this question there, check. Which parameter is constant? If temperature is constant, which law has temperature as being constant? Check. Which law has temperature as being constant? Boyle's law. So hence, it means that in this question too, I could still proceed to use what there? Boyle's law. So that's the same answer. Yes. if I choose to use Boyle's law here, I'll have the same answer. Why? Because they say temperature is constant. That's the concept. So let's do two different ways, guys. Let's use a normal solving. Let's use Boyle's law. For Boyle's law, what do we get there? Instead of there, P1, V1 is equal to what there? P2, V2. This is Boyle's law. And then this is the general gas equation. I'm saying I had to bring in this concept. Why? Because it said temperature is constant. Hence, when we get P2 from here, obviously, P2 we got the what there? P1, V1 over there, V2. Give me value. What's P1? Hold on, that's got the 1.0 times 2 power there. 5 times. What's V1? 0.12 all over. What's V2? 0.24 equals, give me numerator, what do you get? Give me numerator, what do you get? Huh? 12,000 all over 0.24. Give me answer. $50,000. My P was in what? Pascal. So 50,000 Pascal. Let's use general gas equation. Put in this value there. From here, this times this. That's V2, V2, T1 is equal to this times this. P1, V1, T2. What's P2 here? Divided by V2, T1 all over V2, T1. This cancel this. I'm that P2 is equal to P1, V1, T2 all over V2, T1 is equal to what's P1 there? 1.0 times the power there, 5. P1, V1, 0.12. T2, 333 all over V2, 0.24. T1, 333. Please multiply numerator. What do you get? Give me numerator. What do you get there? What do you get there? What do you get there? 3, 9, 6, 0, this all over. What do you get here? 79.92. This divide is what do you get? 50,000 Pascal. So observe, when I use general gas equation, when I use Boyle's law, I get the same thing. Why do I have to use Boyle's law here? Because temperature is constant. That's it. These are very related. Go and learn this thing.